My name is Tuesday Kuykendall, and I am the Scientific Instructional Technician for the Materials Science and Engineering Department at the University of Washington. And this is our Focus D8 X Ray Diffractometer. The Bruker D8 Focus X Ray Spectrometer is used to measure the crystal structure of powders or thin film materials. The X-rays are produced in an evacuated tube similar to a cathode ray tube. An applied current heats up a tungsten filament which liberates electrons. The liberated electrons are accelerated by a high voltage and hit a copper target where copper X-rays are generated. The X-rays exit the tube and are incident on the sample from which they are diffracted into a scintillating type detector. The beam passes through a slit which determines the angular width of the beam. Wider slits give more energy but have wider peaks. Smaller slits give less energy but better resolution. The beam also passes through a nickel filter. The nickel filter removes the K-beta energy before the diffracted beam enters the detector. X-rays at angle theta are reflected from internal crystal planes separated by distance d. The Bragg diffraction results from constructive wave interference when the quantity 2d sine theta is an integral number of wavelengths. A fine powder material contains many crystals located at random angles. Certain crystals happen to be oriented so that the X-ray beam, crystal, and detector satisfy Bragg's equation. This causes a signal spike at specific detector angles. It is important to have a sufficient number of crystals to have an even distribution at all possible crystal orientations. During a scan, the detector is rotated over a range of angles to detect bands of diffracted X-rays produced by the correctly aligned crystals within the sample. So now we're going to discuss sample preparation. For X-ray diffractometry, powder diffraction, it is important to have a well-defined polycrystalline material. And the individual particle sizes of your material should be below 45 microns. You need enough to fill one of these wells, and it should be packed in. And what is important is to have enough of each individual crystalline plane so that when the beam hits it at a particular angle, Bragg's equation is satisfied and you get a peak. This is sort of a statistics issue, and so you want to make sure you have plenty of sample so that all those planes are represented. There's two sizes of sample holders here. This is preferred, this large well here, because, as I said, the more particles that you have represented on this surface in all of the various crystal planes, the better your data is going to be. But often most people don't have this much material, and this will work if your material has been prepared correctly. It's just really important to make sure you have a very fine powder. We have sample holders in here in the lab, and once your sample has been prepared properly, you're welcome to come in and use our sample holders. But we ask that you please clean up after you're finished and that they should never leave the lab. Place your sample in the well and just kind of estimate how much you're going to need. You're going to be pressing it down. And you want to make sure that it's filling the well, but it's still flat with the surface of the sample holder. And you just gently scrape off whatever comes out of the well. And you want to keep it cleaned up, because keep in mind you're going to put this in and there's going to be 3 pins on 3 places on the sample holder, and if there's a lot of material underneath there, that's going to actually alter the angle that it's sitting at, and you'll get your positions will be off. Just flatten it down. And that's ready to go. Even though it's loose powder, if you've prepared it correctly, it will actually hold together on its own. To verify that you have that, just kind of tip it up at a 45-degree angle and make sure that it's holding. The sample stage is held in place with a pressure plate. The position of the beam is fixed, and therefore the position in the z-axis must be very accurate. The plane of the sample must be the same as the plane of the sample holder that is defined by 3 pins. Once your sample is loaded, you can close the doors. The doors are leaded glass and are part of the safety circuit in the instrument. So we are generating X-rays, and those are radiation and could be dangerous. radiation doesn't travel very far, it doesn't travel through thick objects, and it doesn't travel through lead. So these are leaded glass, and they have little pins in the handles that will engage mechanical switches in this right in here in the door. And then there's also electronic switches in the door in the bottom and the top. What this does is ensures that when you close the door, all the switches have engaged correctly and that the door is correctly closed. If the door is not correctly closed, it will cause the safety circuit to trip and it'll shut everything down. There's a control panel here and the exact same set of control panels over there. And there's LED lights that ready, on, alarm, and busy. They're all important to note what state they're in. These buttons up here you must never touch. The only button that you ever want to push on this panel is this big green square button, and that's the door open button. To check, to make sure you've done it properly, just check down here and look and verify that the alarm LED has gone off. Two of the mechanical things that are really important to watch for is how you open and close the door, because that can trigger the safety circuit, and also how you load and unload your sample. The reason that we're concerned about the safety circuit is that inside our evacuated tube is our tungsten filament. And this filament has a really high power across it. And just like with a regular light bulb, over time that filament will become brittle and break, and we want to extend that amount of time as much as possible. And so when we bring the current and voltage down, or we bring the current and voltage up, we're doing it slowly so that this filament has a chance to soak and to slowly get up to power. And this will help to extend its lifetime. So now that we've looked at the physical part of the instrument, we're now going to go to the computer, and this is where we do the controlling and where we control the ramp and where we control the power to the tube. This is XRD Commander. This application should always be on. One of the reasons is that the XRD Commander is what is controlling the X-ray diffractometer, and it's also controlling the power. This is where the power is changed by the user, where it says set, and you'll see that right now the black is 40 and 40 kilovolts and milliamps, but the blue indicated here is the status. That's the current status of the power. At 20 kilovolts and 5 milliamps is standby status. If X-ray Commander is not open, it will not go into this standby status, and the tube will be at maximum power for too long. And we want to extend the life of the tube as much as possible, so we want to be able to allow it to go into standby mode. It will do this automatically after 30 minutes of non-use. When you do want to begin, you want to ramp your power up to 40 and 40 kilovolts. It's important not to just hit set right here. You want to ramp it up slowly. So what you want to do is input the values first. And so we're going to ramp the kilovolts up by 10 kilovolts first, leaving the current the same, and then we're going to ramp up the current. So we're going to put in 30 kilovolts and 5 milliamps, and then press the set button. Now we want to wait approximately 30 seconds to a minute between each step to give it time to soak at that power. Alright, so it's been about 30 seconds, so I'm going to go ahead and go to 40 kilovolts and 5 milliamps. Alright, so it's been about 30 seconds. And I'm going to go ahead and ramp this up to 20. So now, let's go ahead up to 30 milliamps. We can run a scan in this window very easily. We just put in the start value, and the x-axis here refers to the position of the detector, and we call it 2 theta. The start button here, this is set already at 25 2 theta, and the stop is at 85 2 theta. We have an increment here. This is in values of 2 theta, and it's set right now at 0.03 2 theta. And then our scan speed, the setting here is 2 seconds per step. If you want to do a standard scan that's similar to what you see in most of the literature, you would have a start value of 10, an end of 90, your increment will be 0.02, and your time will be 1 second. And that's a standard scan. Now the other thing to note, it says shutter and X-ray. The shutter is closed and it's green, which indicates that you can open and close the door. And the power to the X-ray is on. There are buttons here, open, close, on and off, that you do not want to select. If you start to select these manually, there can be problems with the timing in the computer. It's set up to do this automatically. Up here, we have another place where you can actually change the positions of the detector and the sample. Right now, the blue, just like with the power, the blue is the current status of the position, and the black over here is where you want to change it to. Right now it's at 42 and 85, and I'm going to change it to 30 and 60. And there's a little icon up here that says Move Drives. Just press that, and the drives will move to that position. This is not necessary to do to run your scan. When you hit the Start button, it's just going to go to wherever value you have in here. But it is convenient to be able to move the detector and the sample exchanger if it's at a weird angle to start with. So if I run a scan from this window, I can get a perfectly good scan. I can run the standard, or I can do a quick scan, whatever I want. However, this data will not automatically be saved. In order to automatically save data, I need to set up a parameters file and then call that parameters file in the Jobs tab. If you come down here at the bottom, you'll see a number of tabs. So in the Jobs tab, this is where we create our job. Go to the tab, and you can either select the menu and create jobs, or you can select the icon that is the same as the Jobs tab down here. Create jobs. And this dialog has a number of fields in it, but the only three that you care about is sample ID, parameter file, and raw file. In sample ID, this is similar to a header. This is just information that will go in your actual sample. Your parameter file is the parameter file that I'll show you how to set up in just a second. And your raw file is the file where your data will be saved. Running a scan from this window and from your parameters and hitting Start here ensures that the data is saved automatically. What happens is people will go and run a scan here and go to lunch and not get back in time, and someone who's signed up for the instrument right after them will come and run a scan over it, and your data's gone. That doesn't happen if you do it from the Jobs tab. The way to set up a parameters file is in a separate application, and the link to it is on the toolbar down here, and it's called XRD Wizard. When you open up the wizard, you get the quick wizard page, which is fine. The only thing that you really care about is putting your name in here and determining your scan definition, and verifying your generator voltage and current is what you want. Your scan type is locked coupled and continuous. This is the standard way to do it. What this means is that your detector will be following at 2 theta from your sample. You put in your start value and your stop value in 2 theta. Your step size is also in 2 theta. It calculates the number of steps. You put in your time, and it will calculate the total scan time. And this is important because you want to know how long your scan is going to take, and that's an important thing to know when you're reserving your time for the instrument. Also, you can see that generator voltage and current, the default is 40 and 40, which is the maximum. And if you want to change that, you can do that here. So I'm just going to open a file that is for training so you can see what one of those looks like. And so this is a very quick scan. I've got it from 15 to 55, and my step size is 0.5. For purposes of demonstration, that's perfectly fine. If I wanted to do any analysis, though, that would be unreasonable. Most analysis software need a number of data points for a peak in order to even recognize that the peak exists. And so the maximum step size recommended is 0.1, but 0.02 is preferred. So once you've filled all this in, you can just save it as your name, and it'll automatically put the .dql extension on it and save it in the scan parameters file. And I'm going to create a job. And there's a little button here that will take me to the file folders. I want to go up one into parameter files. I'm going to select my training. And then my raw file, select that. And most people have a folder they've created for themselves. And demo. Now, once I've done that, everything is loaded and ready to go. My sample is in the chamber. But the reason I'm not running it right away is that the parameter file's power is for 40 kilovolts and 40 milliamps, but the power that I have in the actual instrument is still 40 and 30. I want to always make sure that the blue, which is the status, matches whatever is in my parameter file before I hit the start button. because the values that are in the parameter file take precedence. So if I'm at 20 and 5 here and I hit start for a parameter file that's 40 and 40, it will automatically ramp the power up to 40/40 without going through the steps. And this is not healthy for the tube. Okay. Now it's actually up to maximum power and I can go ahead and run my sample. I recommend that you wait 5 minutes or so while it's at maximum power. I have run a number of scans at different times after getting it to maximum power and have noticed a small change in maximum intensity. But for now, since we're just doing a demo, I'm just going to go ahead and hit the start button right here. And then the sample ID now is changed to demonstration. It's loaded, automatically loaded my start and stop and increment values, and it's running the scan. And it moved the stage and the detector automatically, so everything is being done automatically. We can see there's a number of peaks already. This is Illumina, which is a NIST standard. This right now is just drawing lines. If I right click in here and select dots, I can actually see the data points. And hopefully you can see right away that this would not be something that would be recognized in analysis software. There's only one data point here. And you really want a minimum of at least 3 on its way up and it's on its way down. So that click indicates that it's finished. Back to dots. The shutter is now open, closed, which means you can open the door, and the power is still on and it's still at 40 and 40. It is not necessary to ramp the power down when you're finished. We want to be able to keep it up if someone's right behind you. It's better for it to stay up than it is to go up and down. But if no one is using it for the rest of the day, we do want it to go into standby mode. So we just leave this open and leave it like it is. You can minimize it, get your data out of your scans, make sure that you remember to fill in the log, and you may remove your sample and you've finished your scan. Your scan file is automatically saved to a scan folder, and we have a shortcut to it on the desktop. What people do is they find their data when it's finished, and with a USB drive, we also have a 3.5-inch floppy and CD, if whatever you have. Just find your sample and save it to whatever drive you have. And this sample can be opened in X-Ray Diffraction software designed for that. So to open the door, there's a big square open door button here. It's the only button you ever want to push. Press it, the alarm light starts to flash, pull the handles out towards you and away. When you're removing your sample, you want to make sure that first that you have a hold of your sample, but there's a little switch under here. Put your thumb outside of there and then flip the switch towards you. Do not resist the temptation to squeeze the switch and the pressure unit together. This pressure unit is hollow aluminum, and if you squeeze it like that, you will bend it. Hang on to your sample, flip the switch, and remove your sample. When your sample's been removed, you can close the doors. No need to slam them. Verify the door's closed by checking the alarm light, and you're finished.